All right, so we'll get started. I'm Pranava, and then Cerise, do you want to introduce yourself as well?
Yeah, I'm sorry. It's nice to meet you all.
All right, so today's session is mostly going over kinetics. So we wanted to ask you guys before we get started if you would prefer doing the content or the passage first. So we're going to go through the warm-up, the homework, and then we have the content or the passage. So because we've been running out of time sometimes after we do the content, we wanted to get your opinions on that. So if you put it in the chat or say it out loud. There's not too many of us today, so we hope you can be more interactive. Okay. No one? All right.
Oh, someone asked if we can do the passage first before content.
Yeah. If no one has any other opinions, we're going to go with that. Okay.
Okay.
Perfect. Then we're going to get started. So just a general introduction, like always, we're a nonprofit in Virginia, always here to help you for anything with Slack or email. And then these sessions are being recorded, like I just said, so you can go back to them later. And then our email is info@premedpeers.org if you have any questions. And if you're not already on the listserv, which I think if you're signed up for the summer session, you should be, you can put your email in the chat. So we'll add you. And then does anyone have any general questions before we get started? Okay. So I told you the structure of the class earlier. These are the overview of the content topics. Does anyone have anything they'd particularly like to focus on? And then if you guys did the end of the chapter homework questions, did you have any that you would like to go over? If not, I picked some out that I thought were more challenging to go over.
Nava, I don't know if you can see the chat, so I'm just going to update you on the chat.
Yeah.
Someone said specifically to go over free body diagrams.
Okay, perfect.
And that's the only thing we have so far specifically.
All right. So no homework questions?
Not yet.
All right. Feel free to stop me at any point if you do think of one, but I'm just going to go over, I think, 5 questions that I picked out. So if you guys can participate and put in your answers, and if you would like to be called on, just like maybe put an asterisk after your answer if you're typing it in the chat, or just feel free to speak out loud and unmute yourself. So the first one I picked out was number 2, which says 1,000-kilogram rocket ship traveling at 100 meters per second is acted upon by an average of 20 kilonewtons applied in the direction of its motion for 8 seconds. What is the change in velocity of the rocket? So if you guys got an answer for that when you did the question, can you please either put it in the chat or say it out loud? Okay, let's see if we can do that.
And we also have a request for going over vectors and scalars, as in like multiplying vectors, and probably vector as well.
All right, so we will do that. So were you guys stuck on how to get started for this question, or just didn't get a chance to do it? If you just didn't do it, I'll skip over it, but if you're stuck on it, we can take some more time to talk about it. Just let me know where you're at so we can get you like the most benefit for this session. Anyone? All right, well then I'll just go over the answer then. So the answer is 160, so always be on the watch for like specific like question stems. So this doesn't say like what is the new velocity, it says like change in velocity. So that means you have to first find the new velocity and then calculate the change in velocity by taking the new velocity minus the old velocity. So you find the new velocity by first finding the acceleration from the formula force equals mass times acceleration, and then acceleration then equals force divided by mass. And then also be on the watch for unit conversions. So this is kilonewtons, so you have to do times 10 to the 3 newtons. Oh, sorry, this shouldn't be there. This newtons over meters. So this should just be 20 times 10 to the 3 newtons divided by 1,000 kilograms should get you 20 meters per second square. And then you just use this formula to get the new velocity and then calculate the change in velocity from that. So I'm just going to keep going unless somebody stops me specifically, but that's that. The next one is an elevator is designed to carry a maximum of 98,000 newtons and to move upward at a speed of 5 meters per second after an initial period of acceleration. What is the relationship between the maximum tension in the elevator cable and the maximum weight of the elevator when the elevator is accelerating upwards? So if you guys have an answer for that, put it in the chat. If you just didn't do these questions, let me know so we don't waste your time. Okay, then I'll just like breeze through this question then. So the answer is A, the tension is greater than 98 newtons. So the reason, the biggest clue here is that there's a period of acceleration, and the acceleration, because the elevator is moving upwards, the acceleration is upwards. So the two forces you have are tension pointing upwards with the cable and the weight of the elevator pointing downwards. So if you have a total acceleration upwards, that means there's a net force upwards, which means the upward force has to be greater than the downward force. So therefore tension has to be greater than the weight. Okay, and the next one, at a place where g equals 9.8 meters per second squared, an object is thrown vertically downward with a speed of 5 meters per second, while a different object is thrown vertically upward with a speed of 10 meters per second. Which object undergoes a greater change in speed in a time of 2 seconds? So this one almost got me, but you have to be careful that it says greater change in speed. So the answer is A, because it's not change in velocity, which would be acceleration. And obviously, if it was change in velocity, then the g is the same, so the acceleration would be same, but it's a little bit different here, the way it's worded. So you have to calculate change in speed, which means you have to use the magnitude of the velocity, not the direction. So the change in velocity is the same for both. It's negative 19.6 because you just do 9.8 meters per second squared times 2 seconds. And you get the final velocity by adding negative 19.6 to 5 and then to 10 to get, oh, so this is negative 5 because it's pointing downwards. And then this is positive 10 because it's thrown upward. So this would be 5 minus 19.6 equals negative 24.6. And then this would be 10 minus 19.6 is negative 9.6. So then to calculate the change in speed, you have to take the absolute values of this final velocities. So it's it becomes 24.6 minus 5, you get 19.5, whereas for this, it's 9.6 minus 10, which would be negative 0.4. So that's where the difference is. You have to watch out that it says change in speed and not change in velocity. Okay, next one. A 10-kilogram wagon rests on a frictionless inclined plane. The plane makes an angle of 30 degrees with the horizontal. Approximately how large is the force required to keep the wagon from sliding down the plane? So the way you do this is you draw your free body diagram, which we'll cover in more detail. So in an inclined plane, this is the kind of free body diagram you need to have. So your gravity force is always pointing straight down. But then what you do for an inclined plane problem, and Cerise has more slides on this later, so we can talk about that more. But you make like this slanted plane your x-axis, and this direction your y-axis. So your x-axis would be mg sine theta is the force acting on the to move the box down the inclined plane, whereas this friction force is stopping the box from moving down the plane. So they have to be equal to each other in order to keep the wagon from sliding down the plane. So you just do mg sine theta. So this is what you're looking for. You're looking for the force required to keep the wagon from sliding down the plane. And it's going to equal mg sine theta, which is 10 times 9.8 sine 30. And I have more slide really quickly on which trigonometry values to memorize. So I think that's something helpful to do as well.
Yes, and someone just asked how you were able to know to use sine and not cosine. So that's also involves like breaking up vectors, right, into components. So that goes with vector math.
All right, last one. Yeah, I can answer that later. I'll hold off on that question for now and address it when we get to the content part of it. Something that's going to be just helpful is just to like know this inclined plane free body diagram in depth, so you don't have to like think too hard about like how to decide which one is sine or which one is cosine. Like, I don't want to say memorize without understanding it, but just know it instead of like spending time on it every time to kind of like derive sine and cosine. Okay, last one. A rock is shot up vertically at the same time that a ball is projected horizontally. If both start from the same height, which one will hit the ground first? So this one is also a little bit tricky, I think, but the answer is that the ball will reach the ground first. So I think it's easiest to imagine with a diagram. So imagine that this is a rock that you shoot vertically, and this is your, was it ball that you throw horizontally? So the rock that you're throwing up, it's going to take some time for it to come back down from like the upward velocity that you gave it. So that's extra time that the ball doesn't have to go through. So therefore, the ball will reach the ground first. And the masses actually don't matter because if you go through like all the math of the kinematics equations, the masses cancel out from both sides of the equation. But in general, in calculating like time of a projectile in motion, masses don't matter. Okay. Then I'll just keep going through my 2 warm-up questions. Which of the following scenarios describes a system that is not in equilibrium? So these aren't homework questions, so I'll give you guys like a minute to think through it and then put your answers in the chat for this. I'll give you guys like 5 more seconds. Do you guys need more time? Is there anyone that has like an idea, even if it's just like a guess, would like to share? Okay, no worries. The answer is a race car driver driving at 200 meters per second along a mile-long circular track. So the tightrope walker balancing on one foot on a wire. That one's actually kind of weird. I don't know how to. I guess you can think about like he has no acceleration like in the x direction or the y direction because because he's just like in static equilibrium. Like he has no velocity, so therefore no acceleration and no force, no net force. And then a skydiver that has deployed his parachute and is falling straight down at 25 meters per second. So this is a constant velocity. And the reason for the constant velocity is that there is acceleration pushing him downwards, which is just gravity. But what the parachute does is also deploys a force upwards. So the force provided by the parachute cancels out with the force of gravity to create no net acceleration. And that's why there is a constant velocity. So, so the race car driver does have a constant velocity, but what's important is that he's going along a circular track. So that's the tricky part. So velocity is a change in direction or speed. So there's no change in speed here, but so it's not constant velocity, it's constant speed because the direction of the velocity is constantly changing when you have a circular track. So because of the constantly changing directions going through the circle, that's why this is not in equilibrium. Last question, that's mine. For a projectile moving in a parabolic path on Earth, which of the following is true? Give you guys another minute to look at this question. Does anyone have an answer for this one? Okay, if not, the answer is the acceleration of the object is constant. So for A, the net force on the object is not zero because the only force that you have on the projectile, if you're ignoring wind resistance, is the force of gravity, which is pointing downwards. So there is a net force pointing downwards. And so that gravity is constant acceleration. So that's why the acceleration of the object is constant. The net force is not tangent to the path of the projectile at any given time. It's always pointing downwards because gravity always points towards the Earth. And then lastly, the acceleration is not zero because it's equal to 9.8 meters per second square. And then I'll let Charisse take over for her questions and the passage. But just let me know when you want me to advance the slides.
Okay, so this question is a bit of math, but it says a rock has a mass of 100 kilograms. A man pushes the rock on its side with a force of 300 newtons, moving the rock If the coefficient of kinetic friction between the rock and the ground is 0.25, what is the net force on the rock? So I'll give you a minute to do it. And important for this question is to use 9.8 for the acceleration due to gravity. I've become accustomed to using 10, but for this question, you have to use 9.8. And then, yeah, if you can drop your answers in the chat, and then I can explain quickly. Okay, does anybody have an answer before I show it, or have Pranava show it rather? Okay, do you want to click to the next slide? So I did not make the free body diagram on PowerPoint, but I can draw it and show it for someone later, or can write this out better for someone if it's confusing. But basically, for this question, I guess what's important is to figure out what numbers you need when. So because it's asking for the net force on the rock, you know that because it's just moving to its side, the only forces that you're worried about really are the force of friction and the force from the man pushing the rock. But in order to get the force of friction, you need to get the normal force. So in order to get the normal force, you can use the mass and the acceleration due to gravity to get the force of gravity. And because the rock isn't moving up or down on the ground, you know that the normal force is just the opposite. It's equal to the force of gravity, right? So that's 100 kilograms times 9.8. So that gives you 980 newtons. And then to get the normal force, you multiply that by the coefficient of kinetic friction. So that will give you 245 newtons. So now you know that the force due to friction is 245 newtons, and the man is pushing it to the side at 300 newtons. So you need the difference between those two numbers, which is 55 newtons. And again, I can write that out and explain it to someone if they would prefer it visually later. Can you switch to the next slide? Thank you. So this is kind of just a fundamental question that we've covered a bit already, but which of the following expressions represents the normal force on the mass due to the inclined plane? So this is a good spot to kind of practice the free body diagrams. And I'll just give you like 30 seconds quickly. And if you know the answer, you can drop it in the chat again. Okay, does anybody want to guess or give the answer? Okay, do you want to switch to the next slide? Yeah, so someone just said mg cosine theta, and that is correct. So this is, again, a really good spot to practice just kind of knowing that free body diagram. But this is also ties in with vector math, which Pranava will be covering. But essentially, the goal of this question is just you need to remember how to break the force of gravity into its different components. So if you can imagine a line, Pranava, can you switch back perhaps to the inclined plane figure, if possible? Yeah, thank you. So, Yeah, so if you see in this picture, there's the line MG, which goes straight down. And if it helps you, which it sometimes helps me, the line that's labeled MG sine theta, it's just kind of shifted up from being like attached to the MG cosine theta line, if this makes sense. So they could, usually the way that I draw them, they make another triangle. And that helps me remember because that's how you add vectors, right? Is like tip to tail. Um, but so you can see that again in this diagram, to get mg cosine theta, you can see the line that says mg. The angle between mg and the line that's labeled mg cosine theta, that's the theta that we're referring to. And so that theta is the same as the angle of the inclined plane, and that's just like a lot of trig relations. And so then cosine theta would be the adjacent over the hypotenuse. So to get the value of that piece, like that component, you have to do mg cosine theta. And if that doesn't make sense, we can explain that more later. So Pranava, do you want to do, should we move on to the passage?
Yeah, that's good.
Okay.
Unless anyone has any questions beforehand. Sorry. So let me also, Cerise, can you put the link to the Khan Academy passage in the chat as well? So
Yes.
if they want to go to it directly.
Yes, let me just copy it quickly. All right, loading. So okay, I'm sending, so this is the link to the passage that's pictured. And if you do the passage actually through Khan Academy, it will tell you right away if you're wrong or right. So if you think that that would be helpful, you can do it through Khan Academy.
So I think we can give you guys like 10 minutes, or is that too much? Should we, what do you think, Cerise?
Let me just look at the questions again really quickly and see how much math they need. I think maybe like 7 minutes.
Okay, sounds good. So we'll come back together at like 6:38-ish.
Mm-hmm.
All right, and then feel free at any time to like put any questions in the chat if you're getting stuck. Yeah, see you guys then.
Okay. Is everyone ready? Pranava, are you ready to flip slides for me?
Yeah.
Okay. So do you want to click to the next one? Although I'm realizing, okay, so this question asks so it says that the kidney stone is moving towards the bladder with constant velocity and asks how the magnitude of the forces compare. And if you guys, sorry, it was my timer for 11:38. If you guys did it through Khan Academy, it'll auto correct you. So if you want to click ahead, Pranava. So this is a question about Newton's first and Newton's second laws. So we know that F equals ma, right? So if there is constant velocity, then that means that acceleration is 0, which means that the net force on the kidney stone must be 0. So because there is no net force, the magnitude of the two forces must be equal. So this is just kind of careful reading. Noticing constant velocity is always really helpful for these types of questions. And then applying that using Newton's second law. So if you want to go to the next question. So this question, so it's hard because we're not looking at the graph, but if you remember F2, or at the figure, excuse me. I think it's fine. So F2, I can pull it up on my side. So F2 is the force towards the bladder, and F1 is the force towards the kidney. So in this question, it gives you the forces and then asks what the acceleration of the kidney stone would be. Did anybody get the answer or want to drop it in the chat? Otherwise, I'll have you click ahead just so we have time for content. So the first way that I would approach this problem is picking a direction, because that just makes your life easier. So because you know that F2 is greater than F1, we know that the kidney stone must be accelerating towards the bladder because that's the direction that F2 is pushing. So that makes the question twice as easy because now you only have two options. And so then to get the actual value of the acceleration, you need to take the difference between the two forces. So in this case, that would be 0.03 newtons. And I think you just divide that, and you divide that by the mass, which is 0.0015 kilograms. And so this question is nice because they've kept it in standard units, but this question could very easily be made a bit more tricky by giving you the mass in grams instead of kilograms. And so it's just important to keep an eye on those units if you're working with kind of smaller things. And then do you want to go to the next question? So this just poses two more forces and asks if it's possible for the kidney stone to be moving towards the bladder. Do you want to just click to the answer? So again, remember that F2 is the force towards the bladder and F1 is the force going towards the kidney. And this question actually got me at first, I'll admit, but it's important to remember this question is really good at testing our knowledge of like net forces and what acceleration actually means. I think we tend to think of acceleration as always speeding up towards something, but acceleration can also mean slowing down. And that's exactly what this question tests, right? So F2 is smaller in magnitude than F1, but that doesn't mean that the kidney stone must be moving towards the kidney. It just means that if it was moving towards the bladder, it has to be slowing down because the force that is pushing it towards the kidney is greater in magnitude than the force pushing it towards the bladder. So if it was originally in the direction of being pushed towards the bladder, now it is slowing down. So it's possible, but it has to be slowing down. Okay, next question. So this one asks, it gives you what F1 would be and asks what the force would be exerted from fluid buildup. Did anybody answer this one? Did you guys make it this far? Yes, no? I'll have you go to the next one, Pranava. So this is just a Newton's third law question, and it kind of seems, these are the types of questions where you see them and perhaps they seem obvious after you see the answer. But this one is just testing your knowledge of Newton's third law. So assuming that there is one force exerted like on the kidney stone by fluid buildup, then there's an equal and opposite force of 0.06 newtons. And then last question. So which of the following would make the kidney stone harder to pass? Does anybody want to give an answer? Otherwise, I'll just go ahead. Okay, do you want to click ahead? So this is a question applying our knowledge of the normal force and friction. So we know that something that would make the kidney stone harder to pass would be friction between the kidney stone and the kidney stone and anything really, but like the kidney stone and the ureter wall. So then we have to kind of consider like what would increase friction in this case. And so the only way to increase friction is to increase the normal force. So that makes A the right answer, because a greater normal force between the ureter wall and kidney stone would lead to, in turn, a greater force of friction. Okay, so that is the passage. And I just was going to point out that I put a screenshot of my answer to question 3 in the chat. So if that isn't helpful, let me know, and we can also explain it more. But there's a picture if you want to look at it for whoever asked about that in the meantime. Yeah, so do we want to go to content then, Pranava?
Yeah, so it was free body diagrams, vectors and scalars, and how to get like sine and cosine for the gravity.
Yeah.
Did I miss anything else? Can you guys let me know if I did?
Or add things if you have anything else you'd like to add.
Mm-hmm. Or any questions on the passage that Cerise just went over. Right. Until then, I'm gonna go to like these 3 slides that I think covers everything. Sorry, let me stop and reshare for a second. Sorry about that. Okay, you can see my slides still, right?
Yep.
Oh, okay. So we'll talk about like how to do a free body diagram in the context of this inclined plane, and use this inclined plane to kind of cover like vectors, scalars, and like how to get the sine and cosine. So if you have specific questions about like what you're struggling with in a free body diagram, either like speak up about it or put it in the chat so we can tailor like what we say to what you actually need. But in general, when you have a free body diagram, you're trying to just put all your forces that are acting on your object on the paper to see like what's causing equilibrium, or what's causing like a net force and therefore a net acceleration. So for this one, we are assuming it's in equilibrium. So definitionally, in equilibrium, forces cancel out, so there is no net force, which means forces in the x direction. So artificially, when we have an inclined plane problem, we like reorient our x and y directions so that this way, the incline basically becomes our x direction, and then our y direction becomes what's perpendicular to the x direction, so like this way. So then basically forces on the x-axis have to cancel out and forces on the y-axis have to cancel out. So on the x-axis, we have mg sine theta pushing the object down the slope and friction holding it up the slope. So then because this object is in equilibrium, those two have to be equal to each other. And in the y direction, we have normal force, and then the y component of the gravity force have to be equal to each other so that they can cancel out to give no net force. So the free body diagram basically accounts for all of that. And you have to take any information that they give you in words and to put it on this. So for example, if I were to add, say, the object on the ramp is attached to another object with a rope, that's going to be a tension force, for example, over here, and you would have to account for that as well. I think, let's see, who was it that asked about this? Ngozi, do you have any more questions about this one in particular? Free body diagrams, did that help?
I'll just add, I'm dropping like the way that I was trying to explain it before, if it helps you to see the like tip to tail, which I think Pranav was about to go over. I just drew that out and sent a picture in the chat too. So if that helps, you can look at that.
Yep. Yeah, that one's actually like helps a lot more than. All right, so first we have now moving on to like scalar and vectors. So I'm not sure what you guys meant earlier. I think it was Leslie asking about like vector multiplication. That's not something you have to deal with on the MCAT, but what you have to do is break up like a composite vector, like the total vector into like its y and x components maybe. And so all you need for that is like your basic trig functions. Know that sine is the side opposite to the angle over the hypotenuse, and then cosine is the side adjacent to the angle over the hypotenuse. So if you guys have forgotten like that basic trig, I would review it. If you have any questions right now, ask so we can clarify that as well. But that's pretty much all you need to break it into the vector components. And then like similarly to the picture that Cerise put in the chat, I drew this out while we were doing the passage. One, to illustrate like the x and y components I was talking about that we orient our inclined plane on. So we would call this our y direction, like this way up and down. And then this way left and right, our x direction. So then I didn't draw any other forces on this diagram except for the gravity force, so it's easier to see and it's less cluttered. But of course, there would be our normal force, and then maybe like a friction force as well, depending on what kind of like incline it is. So we have our gravity force like this because it's always our total gravity force, remember, just always points down. So if we have the center of mass here, it's just going to go straight down from the center of mass. But we need to break it apart into our x and y components to reorient it along our chosen axes. So then if I were to redraw this separately, I have my mg, so my total gravity force here, and then our angle is over here, and this is our y component of gravity, which would be equal to the normal force. If there is no net acceleration up and down the y-axis, which there never is. And then here we have our x direction of the gravity force, which can have acceleration up and down the slope, or it can be in equilibrium if there's another force opposing it. So so it's just the same concept as this. So sine is, remember, the side opposite to the angle. So the side opposite to the angle over the hypotenuse. So here we have our angle. So when you're doing sine theta, it has to be opposite to that angle. So that's going to be your fx component of gravity over the hypotenuse, which is mg. So then it's just you rearranging to isolate for the x component of gravity to get mg sine theta. And then cosine is the same thing. Remember, it's the sine side adjacent to the angle over the hypotenuse. So when you have the angle up here, the side adjacent to the angle is FGY. So then it becomes cosine theta equals the side adjacent to the angle over hypotenuse, which is mg, and then you rearrange the same thing. So this is how you get that mg cosine theta here, and then mg sine theta here. So imagine if your angle is in this like little nook right here, the side adjacent is going to be this one. It's going to be mg cosine theta. So the side opposite would be like here, but then we just kind of like relocated up here to put it on like the same starting point as the other forces. So this would actually be the same thing as what we draw down here for that triangle. See any questions? Somebody put a little mnemonic in the chat to remember sine and cosine, if that's helpful to everyone. Thank you for that. But did that help to anyone who asked to focus on these topics? Okay, then any questions in general, or yeah. I don't think we have like too much time left. We have about 5 minutes. If anyone, I can go back to like the original content like summary slide if you see anything newly now.
And the slides are available to everyone, right? Or they get shared with everyone too?
Yeah, they will be. I don't think we have uploaded any yet, but yeah, they will be available. So will be the recording. So you can listen to our explanations later if you missed anything. Yeah. Feel free to ask any questions if you have any, or give us feedback or suggestions as well. If not, you guys are welcome to go right now. Definitely go through the rest of the content slides that we didn't get to, because I think it's pretty useful what we like gathered. For example, let's just keep talking while people leave or not. Like we have like some of the trigonometry stuff that we talked about like kind of more neatly, and here's like the angles that you need to memorize like the decimal versions of these as well. Vector addition, the base units to memorize, derived units to memorize, like stuff like that. Thank you for coming. Have a good night. Yeah. And then if you have any questions after you go through the content slides, you can always message us in Slack or use our email to follow up. Or I guess now you can chat in Teams as well. Okay. I'm going to go ahead and stop the recording now.